Hello, this is Kandai Watanabe. I'll now like to talk about my project implementation of a linear model predictive controller. A model predictive controller is often compared with linear quadratic regulator controller because they have similar formulations in common. Both controllers compute an optimal input U with respect to an objective function, and these controllers are called optimal controllers. Here, throughout this implementation, I will use a drone as an example model. In such case, input U is a force and torques applied to the drone. Drone uses four rotors to compute its upward force and its torques. On the left, we have a LQR controller implemented. LQR only considers state at current time t. Therefore, it fails to plan ahead, and so it is unable to track to the original trajectory. However, the MPC controller considers future steps from current time step t to large t in the future. And therefore, it can plan ahead and compute an optimal policy so that it can track the reference trajectory. Now I will talk about how LQR and MPC controller work. A linear quadratic regulator's objective is to minimize the linear quadratic constraint state cost and input cost for infinite time horizon. A state is the system state whose motion is governed by its physical model, and input is a system input. A physical model is shown on the right. It is linear with respect to its previous state, and input U and disturbance D. Q and R in this objective function are positive definite matrices, which are called weight matrices. They are hyperparameters that decide which variables are more important to be minimized. From this objective, optimal input U can be computed. This objective shows that it wants to minimize the error between the states in the reference states for infinite time horizons. In other words, the solution should be optimal for all time in the future. However, it is difficult to consider all reference states in the future. Thus, by setting the reference state and solve it as a linear quadratic regulator problem, then an optimal solution can be computed analytically. By solving the problem, we get a feedback gain k. And this feedback gain is stationary and is optimal under this assumption. Disadvantages are that input is only independent on current time step t, and therefore it cannot consider reference trajectory into account. To conclude, the LQR is a stationary policy and MPC is a non-stationary policy. In other words, the policy changes over time. The difference in the formulation is just that LQR solves an infinite time horizon problem, whereas MPC solves the finite horizon problem at every time step t. It can be seen that since LQR only uses the current state for computing the input U, it only considers it is stated that it can be seen that it only considers the current state. But it can be stated, but for the MPC, it can be stated that it can take future steps into consideration. Now I will talk about how MPC can be formulated into a quadratic programming problem. The objective of MPC was to minimize errors between predictive and reference states and inputs. How do we get the future states and inputs? The predicted states can be computed by rolling out the dynamics model with a random input U. Like in the figure, xk plus 1 can be computed from xk using the dynamical model. And the dynamical model can be derived from the Newton's second law and rewrite it in the similar manner as on the right. So f equals ma can be rewritten as a equals f over m, and this x2 dots can be converted into a this one first order derivative. And however, one should be careful since this is a continuous state. You need to discretize based on the sample time. And once dynamical model is derived, the future states can be predicted by rolling out the model with the random inputs as shown in the equation on the bottom left. Then the model can be augmented, and the final model then will look like the one on the bottom right. Based on this model, we minimize the objective function. If inputs are decided, and also the disturbance in this case, then the state x, future state x, is determined as shown on the equation on the bottom right. And the idea to solve this problem is that we optimize this input u by minimizing the error between these predictive states and the reference states iteratively. So the objective function in MPC can be written as the first equation, as in the first equation. We do not have the integral in this equation, but they are included in the augmented states and inputs. And Q and R are weights matrices, which are also augmented. And by substituting y into the original objective function, we can rewrite this equation. And here, the measured state y is a measured state and is assumed to be equal to the state x for now, and which means all states can be measured. The computation looks complicated, but if we simplify the equation, at the end we get a linear quadratic cost. As stated before, the error is only dependent on the input. And so if we optimize this objective with respect to u, we get an optimum policy u asterisk. To wrap up what we have looked so far, MPC formalization is organized as follows. Discrete system model can be written as in the first equation. And discrete, here in our problem, I added a gravity vector into disturbance decay so that we can take gravity into account. Since we have this model, we can predict its future states by inputting random inputs as explained. By rolling out, we get an augmented model where xk is a state, uk is an input, dk is a disturbance, yk is observed state, and q and r are weight matrices. And large F is an augmented states matrix of A, and then G is augmented inputs matrices, and S is augmented matrices, disturbance matrices. Yep. And assuming that everything can be observed, which means H is equal to identity matrix, thus then we get the predictive measured state Y2. And then in MPC, our objective is to minimize the quadratic cost of states and inputs by substituting Y into the original objective function as shown in the last equation. We can then have an objective function that is only dependent on inputs u. The original problem is then turned into a quadratic form. This is clearly a quadratic problem, and since this is a quadratic problem, we can also add a linear constraint, like gx is less than or equal to h, and also ax is equal to b, as in linear programming, where p and q are shown as on the bottom. For example, we can add constraints, and constraint on inputs can easily be added. For example, if you want the force to be in a range of 10 newtons, then you can set a constraint like this. And likewise, we can add constraints to the inputs very easily. Constraints on the state can also be added, but need some tweak. Since all objectives are written in regard of u, we need to rewrite the constraint. For example, if velocity has a limit of 10 meter per second, one can write like this in the second equation. But since x can be written with respect to u, we can sub this x into the constraint, and we get the last equation. Now I will show the simulation result. For simulation, I used a nonlinear model, and for the controller, I used a linear model. All the parameters are shown on the right. We also added constraints on the angles. Phi and theta should be within plus minus 0.15 radian. The resulting animations are shown below. As stated before, LQR is unable to track the reference trajectory, but MPC is able to track the reference trajectory. When we also look at the data, it clearly shows that the constraint is met. The angles phi and theta do not go over the constraint values. Likewise, we can add more constraint to the problem so that it can meet the specifications of the problem, a system design. And this is the end of my simulation and result. The code is on my GitHub, and it can be installed using just pip install. And I am currently working on extending this library so that it can incorporate both control and reinforcement learning problems at the same time with different kinds of agents and environments. For RL, we can incorporate DQN, DDPG, anything. And then for the control side, we can add IQR, DDP, and CEM. And for the environment, we can choose to add OpenAI Gym or our original environment. I made this framework because the framework does look same. The problem does look same between RL and control. It's just that RL has train function separately and sets train loop separately. However, to interact with the environment, the control agent and RL agent do look the same, and I wanted to compare with these two different kinds of methods. I made this library. And you can also add your own policy, controller, and environment if you want to. Please feel free to contact me if you're interested in this project. Thank you.